Okay, welcome to yet more integration practice. So we're going to start off with an obvious substitution problem. Obvious because we're given the substitution. So where do we go from here? Well, if x equals 2 cos u, we're obviously interested in x squared. So x squared would be equal to 4 cos squared u. And dx by du is another obvious one to go for. So dx by du is equal to minus 2 sine u. Okay, now I'm differentiating that one. We can also do the limits. So if x equals root 2, then we end up with 2 cos u equaling root 2, which rearranges into cos u equals 1 over root 2, and that gives us u equaling pi by 4. And the other limit, if x equals 1, then of course that means 2 cos u equals 1. Cos u is going to be a half, and that means that u equals pi by 3. So there's our limits. Okay, right, let's get to substituting this monster. So there's our integral. So the 1 is going to go to pi by 3, and the root 2 is going to go to pi by 4, and we're going to have a 1 on the top, and on the bottom we're going to have a 4 cos squared u coming from up here, and then underneath here we have the square root of 4 minus 4 cos squared u. Okay, now we need to substitute for the dx, so let's rearrange this for dx. So dx is going to be equal to minus 2 sine u times du. I'll just multiply the d up. So dx, so I'm going to replace this with minus 2 times minus 2 sine u du. Just put it in brackets to make sure it's obvious it's a multiplied by the negative 2, it's not being subtracted. Right. Well, that's a bit of a monster, isn't it? What to do with that? Well, I think the clue here is under here. What we've got here is something which is a rearrangement of one of the trig identities. So if we start with sine squared x plus cos squared x equals 1, then you can see that sine squared x equals 1 minus cos squared x, which of course is what we've got here. In fact, what we've got here is the equivalent of 4 sine squared x is equal to 4 minus 4 cos squared x. So we're going to use that to make our substitution. We're going to replace this 4 minus 4 cos squared u with 4 sine squared u. So let's do it again. Make sure you don't lose anything. It's tempting, I know, to just shortcut it all. Right, we've got 4 cos squared u, and then here we've got the square root of 4 sine squared u, and then we've still got our minus 2 sine u du. Right. Okay, next step. My integral sign seems to be diminishing each time, pi by 4. Okay, I'm going to bring the minus sign out the front. I'm going to stick the 2 on the top. I've got my 4 cos squared u. Now if you square this, the square root of the 4 is going to give us 2. Square root of the sine squared is going to give us sine. And I've got my sine u there. And you can see that that's going to go, and that's going to go, leaving us with a 1 on top. And then my final messing around here, I'm going to switch the integral limits and get rid of the minus sign. So I've got pi by 4 at the bottom, and pi by 3 at the top. And if you think about when you evaluate limits and the order in which you subtract, you can see why that works. Okay, so we're going to have 1 on the top, 4 cos squared u du. Now, we can't do cos squared u, but it is on the bottom, which means it's actually not a cos squared u at all. See, you were thinking it was a cos squared u all this time. It's actually, oh, we've still got the quarter, but it's actually a sec squared du. Okay, and we can now finally integrate that. So let's have the quarter outside of the integral. Sec squared goes to tan, so it's tan u, and then the limits, pi by 4 and pi by 3. Okay, which gives us a quarter times tan of pi by 3 minus tan of pi by 4, pardon me, which leaves us with a quarter of pi by 3, tan of pi by 3 is root 3, tan of pi by 4 is 1, and that's it. Job done. Well done if you managed that. Again, if your layout is significantly different from mine, then you should be looking to follow this sort of process. Obviously, if I had more paper, I'd be going down the page here. Okay. Right, well, let's hope this one's a bit easier, eh? Okay, so what we've got here is obviously a parts problem. We've got our x function and in this case, an ln function. So integration by parts. So let's start off with u. Now, u is normally the x unless there's an ln around. So in this case, it's an ln of x, which means that the du by dx is 1 over x. Now, that makes our dv by dx the x squared, which means that the v is x cubed over 3. And then we can substitute into the parts formula. So it starts off with uv. So that's these two multiplied. So x cubed over 3, and then ln x. Okay, minus the integral of v du. So this is a bit more complicated than normal. There's our v, and our du is 1 over x. With respect to x, that is going to cancel with that, leaving us squared. So just tidying that up, x cubed over 3 ln x minus the integral of x squared over 3. In fact, let's take the third out with respect to x. Okay, and then we've got x cubed over 3 ln x minus a third. X squared goes to x cubed over 3 plus c. Don't forget that. And to finish off, we'll just smarten that little fraction up a little bit. So we're going to minus x cubed over 9 plus c. And that's that one. That was a lot easier than the last one, wasn't it? Okay, almost there. Right, what's this one? Well, this one, to me, looks like a substitution problem. Although it could be a standard pattern problem. In fact, it certainly is a standard pattern problem. I'm going to treat it as a substitution. But you could treat this as a standard pattern in that what you've got here, if you've got f of x on the bottom, you've got f dash of x on the top, so you could use that pattern. Okay, so here's my substitution. I'm going to let u equal e to the 2x plus 1, which makes du by dx 2e to the 2x. Okay, so we have got the integral of e to the 2x over u. Let's substitute for the dx now. So the dx will have to go up. So du divided by 2e to the 2x equals dx, which means that we have here a du and a 2e to the 2x, and you can see that they're going to vanish off like that, leaving us with the integral of 1 over 2u du. Okay, and you could bring the half out at this stage if you liked, and that's a half ln u don't forget it, plus c. And since this is not not got limits, it's an indefinite integral, I'm actually going to put it back in terms of x. So we've got ln of, and u is e to the 2x plus 1 in this case, and now plus c. And there we are, we have it. Okay. Finishing off with a nice little one here. Okay, so cot squared x is not in your standard functions, just like sine squared x and cos squared x. And if you want to integrate one of these, you need to find an appropriate trig identity to turn it into something you can integrate. So in this case, the identity we're going to use is cot squared x plus 1 equals cosec squared x, which of course is just a rewriting of this. So if you divide that all through by cos squared x, you'll end up with the one that I've just written down. So we are going to change this from a cot into a cosec minus 1. So cosec squared x minus 1 with respect to x. And now it's nice and easy because cosec squared x is a standard integral. It goes to minus cot x, minus 1 goes to x, and don't forget the plus c at the end. And that is the end of number 4. Good luck.